In this video, we're going to look at workload management, which is the control of resources for different types of workloads on a data solution. A data solution typically must meet certain service level agreements, or SLAs, meaning that a given process is expected to execute within a certain window of time. Now, when I say process, I'm referring to a complete data workload process, which consists of one or all of the following: loading the data into the system, transforming the data into a suitable state and format, and querying the data. In today's distributed systems, a data solution might handle hundreds or thousands of these processes in parallel, assigning resources to manage them. The distribution of resources to perform these processes will determine the length of processing time. So to meet SLAs per process, a workload management system must be able to isolate and control the resources assigned to each process, even though the processes might be sharing physical resources under the hood. So now let's talk about a data warehouse, which is what many organizations use to manage and report on their data. And let's discuss what's involved in its workload. Let me clarify the difference between a database and a data warehouse. A database is an instance, like SQL Server, that typically stores one type of data. A data warehouse, on the other hand, typically stores data from many sources and allows that data to be combined in complex ways for reporting. It may include a database such as SQL Server, but also supporting services. When we talk about a data warehouse workload, then, it includes all of the following: the process of loading data. In the case of a data warehouse using SQL Server, this may be an external process that loads data directly into SQL Server or into another process or processes that are in between. Performing analysis and reporting. So this is all the servicing done to allow users to query the data and also generate reports. Managing the data. In a distributed cloud system, this may involve moving or replicating the data between regions, for instance. And exporting the data. For example, to archive data in a data lake or to move the data to another repository. So if a data warehouse is managing multiple workloads, how can you control workload resources? Well, as an example, we can look at Azure's warehousing solution, Synapse Analytics. Synapse Analytics querying language, Synapse SQL, allows you to assign resource classes. This assigns memory resource to the query based on a role membership associated to the user making the query. For example, if you were making a query as a user with the role static RC10, your query would be assigned a static amount of memory, regardless of the query. These roles allow resource classes that have differing amounts of static memory per query, as well as memory allocation as a percentage of the entire available memory, tuned for small, medium, large, or extra large queries. Some challenges of this type of memory allocation for queries is that the query can't be governed directly. So for example, even if a query was in a resource class to guarantee 10% of the available memory, if it was an intensive query, it could still end up taking 100%. So it doesn't allow direct control of the workload. A more advanced form of controlling workload resources came with dedicated SQL pools. With dedicated SQL pools, workloads are assigned resources using three concepts: workload classification, which assigns a workload to a specific workload group. Now, workload classification also involves setting the workload importance, which controls whether the workload gets resources before other workloads. And workload isolation, which is a way to guarantee dedicated resources for critical workloads. So let's look at how workloads are classified in Synapse SQL. Originally, with resource classes, the special function sp_add_role_member would be called to add the member calling the query to the appropriate resource class role. As mentioned, this had its limitations, one main one being that you couldn't dedicate memory to a critical workload. Instead, all workloads competed to some degree for the resources. With the newer create workload classifier method, you create a classifier which runs for every incoming request, and allows more fine-grained control of resource allocation per workload. As mentioned, dedicated SQL pools allow for workload isolation depending on the workload group that a request comes in on. With workload isolation, resources are held exclusively and can't be used by any other workload until the execution is complete. This guarantees execution performance for critical workloads that have to complete under a strict SLA. With workload isolation, you can define resource amounts per request. Another thing you can do is not only reserve resources for a workload, but also cap what resources they do use to prevent a workload from starving other workloads. This gives you a high degree of control over the resources used per workload. And finally, workload isolation can be used to apply other rules related to workflows, such as query timeouts, allowing yet another layer of workflow control. Data is at the center of the power of today's cloud solutions. More and more, organizations are realizing the valuable insights that are hidden in their data stores, waiting to be discovered. Because of this, cloud providers offer a large range of services for collecting data from many different data sources, such as IoT devices, tools for analyzing that data to mine business insights and present them in a way that's clear, and storage, particularly big data storage, which is capable of storing massive amounts of data for analysis. In this video, we're going to look at data solutions that help organizations make the most of all that data. First, let's take a moment to define just what we mean by data. Really, data is anything that supports valuable business analysis. In a more concrete way, though, data is typically in the form of numbers, descriptions such as strings, and even observations, such as data entered by a user as a response to some incident. Data can be structured, such as tabular data in a SQL database. This has a known structure or schema and follows strict rules. Semi-structured data is data that has structure in that there are meaningful fields, but it doesn't follow the structure of a relational database table. A perfect example is NoSQL, in which records are often just JSON objects that contain properties as fields. And finally, there's unstructured data, which has no preconceived data structure. A good example here is PDF, image, and sound files stored together in a data store. Algorithmic services could scan these very different data forms to look for meaningful data patterns, but the data is not necessarily structured in a way conducive to such a search. So as mentioned, structured data is data that's tabular. It has predefined rows and columns. A relational database, such as SQL Server, is a perfect example. It has organized sets of data. The databases and tables, or schema, are defined in the database before the data is stored. In structured data, you know the format of the stored records ahead of time. Now, this implies that any process populating a relational database knows the structure of the data ahead of time. If data is coming into the system that's not of the proper format, it would have to be transformed before reaching the database. Then there's semi-structured data. One example of this is a key value store. Microsoft Cosmos DB is an example of a key value store. Every record is referenced by a unique key. There are no inherent predefined relationships among these records, and hence it's not relational. Think of a big flat list of records, every one with a unique key used to reference it. In Cosmos DB, records are stored as JSON objects, and each record can have different fields. So unlike a traditional relational database like SQL Server, in which the schema of the tables is strict and defined before the data is stored, in Cosmos DB the format of records is dynamic and completely defined within the record itself. This allows you to store data without knowing its structure or fields ahead of time. It can also make analyzing the data more challenging, since analysis services might not know what the schema of individual records are. For instance, If a report relies on a field called outdoor temperature, what if certain records don't have that field? Analysis tools designed for semi-structured data usually either selectively ignore data that doesn't have the fields needed for analysis, or works on agreed-upon conventions as to what fields the data will contain. Another example of semi-structured data are graph databases, which store data in the form of a mathematical graph. The records in a graph database represent nodes of a graph, and they contain relationships to one another. Like a key value store, the schema in a graph database is not predefined, but is rather dynamic and stored in the records themselves. A graph database is excellent for doing analysis on data with many dynamic associations. I've used graphic databases to store models of industrial plants, for example, where a plant might contain many subsites, each of which contains pipes and tanks. This can all be modeled as associated records in a graph database. Cloud providers typically have different solutions available for the different types of data. For structured data, Microsoft Azure has the Azure SQL Database instance. This can be deployed in Azure in minutes and runs in the cloud, although you can access it remotely via tools such as Azure's Data Studio or Microsoft SQL Server Management Studio. You can create and access relational tables using queries in the same way you do for an on-site SQL Server instance. The main difference is that everything is managed and run for you by Azure. All you need to do is specify a database server, which is another resource available from and managed by Azure, and then provision your schema. Once you have your SQL Server database instance provisioned in Azure, you need to give users permission to the data within it. This can be done using Azure Active Directory to control access for Azure users, and you can also control user access via roles assigned to users provisioned in the database itself. There are three forms of access. Read-only access, which you can assign to users and accounts who should only view data but never change it. For example, the account for a read-only report would have this level of access. Then there's read-write access, for accounts and users that should be able to read but also modify the data. A service that's collecting data and writing it to the database would typically have this access. And finally, there's owner privilege, which gives full access. Now, this should only be used for administrative users and accounts, because it allows for managing database schema and other users and roles. So to complete the discussion of Azure storage for different data, both Azure Table Storage and Azure Cosmos DB are examples of cloud databases that store semi-structured data, and Azure Blob Storage stores unstructured data. Today's cloud services offer flexible data storage options that cater to not only how data is stored, but how it's used. In this video, we're going to look at Azure Data Storage Services. We'll discuss what type of data they store and how that data might be used. We'll also look at security with Azure Storage Services. So first, it's important to understand that data storage comes in two broad categories. There's relational data storage. This is storage like SQL Server. Relational storage is organized in schema or databases, tables, and fields. These tables can have relational associations, hence the relational aspect. One of the big upsides of relational data storage is that it has a predefined structure in its schema, which queries can rely on. Relational tables are also efficient if they're designed to minimize duplication of data. For example, if a table stores a person's eye color as a string, then the words brown or blue will be duplicated once for every person with that eye color in the table. It's possible in a relational database to have a separate eye color table with all the known eye colors as records, and all the records in the original table can simply refer to the eye color table rather than repeating the strings. This is called normalizing, and it avoids duplication of data. The downside of a relational database is that its schema is rigid, so it can't store any data that's not in the schema. The other type of data storage is non-relational. This includes any data storage that doesn't meet the relational table structure of relational databases. NoSQL is an example of this. With NoSQL, data records are typically stored as JSON objects, and there's no set schema. Each record can have its own unique properties or fields. NoSQL is good for storing irregular data, or storing data without transforming it first. Its downside is that it can be difficult to query because you can't always predict the record fields. NoSQL databases are popular with cloud development because they're more flexible and can be very fast. Data duplication, avoided in relational databases via normalization, is actually used in NoSQL databases as a strategy to speed up queries. Now we're going to look at Azure Storage Services, which are non-relational in nature, and therefore are flexible enough to be used for just about any type of data imaginable. There's scalable services which you can deploy in Azure in a few minutes, and they're fully managed by Microsoft on your behalf. We'll be looking at all the core Azure Storage Services, but it's worth noting that they're not all databases. For example, one of them is disk storage, which offers disk storage for Azure virtual machines. So why use Azure Data Storage Services? Well, let's look at some of their advantages. Azure Storage Services are highly available. Microsoft creates redundancy for your data under the hood, so if there's a loss of connection to one instance of your data, it's very likely that another redundant instance can take its place and your customers may not even notice. You can also choose to replicate your data among regions to make access in different parts of the world faster, or store duplicates in different data centers to protect your data in case of a localized catastrophe like a flood. This can all be done online by choosing options when you're deploying through the Azure portal, or in some cases, by changing your configuration after you've deployed. By using Azure, you're automatically covered by all of Microsoft's various security measures. This means your data security is included in the price of the storage service. You can take advantage of the scalability of serverless cloud technologies. For instance, each table in Azure Table Storage can store up to 500 terabytes of data. And if you need more room, you can spool up more tables without worrying about hardware, which is managed by Microsoft. As I've alluded to several times now, the actual running of your storage services is all managed by Microsoft, so you don't have to worry about infrastructure or scaling. The Azure storage services are accessible via the web, so you can literally access them anywhere in the world, and you can interact with them via computer languages such as C# or Python, as well as script languages such as Azure CLI or PowerShell. So now it's time to look in some detail at the core storage services themselves. First, there's Azure Blobs. Azure Blobs are Microsoft's core solution for big data storage in the cloud. Blobs can store data in any format. For example, you can store text files, binary files like sound and images, or even videos. The idea is that incoming data is stored in a blob with little or no transformation. It's just stored as is. Then, when it comes time to analyze the data, data scientists write processes that scour the various formats for meaningful data. For example, they might open pictures and scan them for words, or search PDFs for lists of names. Tags can be used as a simple way to make all of these various files more searchable. Next, we have Azure Files, which is essentially a file sharing service on the cloud. It can be used by your virtual machines or even your on-site machines to share and manage files. All of the files are stored in the Azure cloud. Azure Queues are a way to queue up data in the form of JSON messages. It's often used as a way for services to interact with one another in a decoupled manner. One service pushes a message onto the queue, and the other service can pop it off in the same order that it was pushed. Azure Tables is a NoSQL key-value database, in which you can define tables and store records in them in the form of JSON objects. And finally, as I'd mentioned briefly before, Azure Disks offer block-level storage for Azure virtual machines. All of these storage types take advantage of the benefits of running in the Azure cloud that we looked at earlier. Now that we've looked at the 5 core Azure storage services, Let's talk about how security is managed. The best bet for both security and ease of use is authentication and authorization via Azure Active Directory. Blob and Queue storage services offer role-based access control, or RBAC, via Azure Active Directory. This means that Azure users can be given access via roles that are managed on the service itself by an administrator, via the Azure portal, programmatically, or by script. Azure Files also offers identity-based authorization that can authorize access to files to either Azure Active Directory users for the cloud or an on-premise Active Directory domain service. Blob, File, Queue, and Table services all support authorization with shared key. This is a key that's generated when the storage account is created, which clients need to send via a header when making requests. An administrator can regenerate this key if necessary. A shared key is not as flexible or secure as RBAC, or role-based access control, because it's not associated to an identity. Access to storage resources can also be granted via a shared access signature key, or SAS. A SAS can define restricted access, such as access that expires over time. And finally, in blob storage, there's the concept of making a blob container public, or in other words, granting anonymous access so anyone on the internet can access it. This is fine for some non-sensitive data, such as images that can be publicly distributed, but for most data, it's not feasible. Now, when it comes to security, there's more to consider than who can access what. In Azure, all the core storage services are encrypted at rest, meaning that the data is stored encrypted, and so if it was copied from storage, it would not be able to be read without the proper key, which is not available outside Azure. There's also the concept of client-side encryption. This means that libraries for building client-side applications and services on top of the Azure storage services have methods for encrypting data at the client side, so it's sent on the network encrypted as well. Encryption makes the data even more secure. In this video, we're going to look at a data concept that is very important in many business transactions, and which can also be tricky to manage in today's distributed cloud data systems. This is a transactional workload. A transactional workload may involve several steps, but those steps combined need to be atomic, meaning they behave as a single step. As an example, think of transferring money from one bank to another. We call this a bank transfer and may think of it as a single step. But in the computer system, it's actually two distinct steps: removing the data from the source account and adding it to the destination account. This has to be done as a single transaction. You never want the system left in a state where the money was lost, where it was removed from one account and never added to the other. Either the transaction is completed in whole, or it must fail and leave the system as it was before the transaction took place. In other words, the transaction succeeds or fails as if it were a single step. Relational databases are good at transactional workloads. For example, in SQL Server, you can wrap queries in a transaction, which guarantees that they're executed as a sequence of operations that are either completed successfully as a single unit or undone as a single unit in the instance of a failure. Transactions are started at a defined starting point. Queries can be assigned to the transaction, and they're executed as a single unit once the transaction is closed. So how do transactions work in a transactional database? Well, to be transactional, the database needs to follow four properties. It needs to guarantee atomicity. As I've discussed, the steps in a transaction have to succeed or fail as a single unit, so the system isn't left in an incomplete state. It also needs to guarantee isolation. This means that as multiple transactions run concurrently, they can never access one another's internal or incomplete state, but instead result in the same overall state as if the transactions were run sequentially. As an example, imagine two bank transfers occurring on the same accounts. Transfer A starts, and then, while Transfer A is executing, Transfer B begins. Transfer B cannot consider the balance of accounts when Transfer A has only partially completed, or mistakes could occur. Instead, the end result must be exactly the same as if Transfer A had completed and then Transfer B had run, even though their executions overlapped. These transactions are isolated, therefore, if their executions don't interfere with one another. Transactions require consistency. It should not be possible in a bank transfer for data to be removed from a source account and not appear in a destination account. And finally, the database must guarantee durability. This means that once a transaction is completed, it is not lost, even if there is a system failure. This implies a history of transactions that are permanently stored in a robust way, usually by some backup strategy for the data. It's worth noting here how complicated transactionality can be. Databases that implement transactionality must handle multiple concurrent users, accessing and modifying the same data at the same time, without breaking the rules that we've just discussed. These transactions need to be isolated, which is often done with locks, where other transactions are locked out of the data until the current transaction completes. This is a balance, however, since excessive locks can seriously deteriorate performance. Finally, the system needs to ensure consistency and recoverability in the case that something goes wrong. Just imagine what might happen if bank computers lost account information, or that information became corrupt and it wasn't recoverable. The complexities of transactionality are only compounded by distributed databases, as is common in today's cloud architectures. In distributed databases, data can be stored in multiple computers in the same physical location, or even located over a network of computers that might be widely distributed physically. This adds the complexity of network traffic to the transactionality equation. For this reason, distributed databases have the concept of eventual consistency. To underline this complexity, recall the bank transfer example, and imagine that the source account and destination account are in servers in different countries. The transaction removes the money from the source account, but then the network call to add the money to the destination account fails. What should the system do? Well, it should do what's called a rollback, putting the systems back to the original state before the transaction occurred. But what if, when the system attempts to add the money back to the source account during the rollback, that network call also fails? You can probably see now that this can be tricky. As a compromise, distributed systems have the concept of eventual consistency. When data is replicated in regions around the world, for instance, the transaction is completed in one region and then is eventually propagated to the other regions. Before the propagation, it's possible for someone reading the data in those regions to get an unexpected result. But this guarantees that eventually all systems are consistent. Eventual consistency can be great for inherently unordered processes, such as sending email messages. It's not so great for ordered processes, such as performing rolling aggregate analysis on streaming data. In the case of ordered processes, the equivalent of locks might be used to guarantee synchronous processing of transactions, although this largely defeats the benefits of massively parallel processing that eventual consistency allows. In this video, we're going to look at analytical workloads. Analytical workloads perform data analysis on a read-only, large set of data that's been collected and usually aggregated from the raw data to highlight important business factors. These analytical results are often shown on visualizations, such as tables and charts. For example, a chart showing the trend of quarterly earnings on a business report is an example of an analytical workload. They're used for business decision-making, and they usually don't show large amounts of raw data, but rather summaries or snapshots of the data of interest. Now, some analytical workloads are of a higher importance than others in regards to processing time and therefore resource allocation. For instance, an analytical workload that shows trends of weather on the company website will likely have less importance than the aggregated yearly sales numbers for a report that needs to be available for stakeholders on a specific day. The latter should be given importance because it has a service level agreement associated with it. The yearly sales numbers have to be available on a certain deadline. Microsoft Azure Synapse has a concept of workload importance, which controls the order that SQL pull requests run. These orders are low for the least important requests, such as the weather on the company website, which can be behind and there are no serious consequences. Below normal for slightly more important workloads. For example, the company website might have a count of oil facilities with issues. Perhaps this can be behind as much as a day, but it's relatively important information, so it's higher importance than the current weather. Then there's normal for typical workloads. You might have ad hoc queries by data scientists set to this importance. Then above normal for those with more than normal importance, such as summaries that should be accurate within 10 minutes but are not critical. And finally, high is for those of highest importance, such as the example of yearly sales figures that stakeholders have been promised would be available on a given day at a given time. Importance offers control over the resources used by analytical workloads. Workloads placed in higher importance categories will run before those in lower importance categories. Those placed in the same category will compete for resources. When workloads are not prioritized by importance, there are certain methods that will cause read and write activities to be locked, which will affect what order workflows run. Examples are partition switching, in which data is moved between tables. For example, you may perform a partition switch to move data to an archived data store. The rename object method also causes a lock on the object while it's being renamed. While locks are on the data, other workloads can't run. Within the same importance level, non-locking workloads will be given priority over locking workloads. For example, if a request to rename a table is queued and waiting to be run after the currently running workload, and a non-locking query on that table is submitted, the non-locking query will run after the current workload but before the table rename. Importance allows you to control this. If the rename object method was in a higher importance level than the non-locking query, then the rename would occur first. Now you should note that importance is not the only consideration when making your analytical workloads run as efficiently as possible. You also need to consider the efficiency of the workloads themselves. For example, consider an organization who has oil fields around the world and wants to have a dashboard that rolls up oil production sums by different levels, say by well, by field, by general region, and then global totals. Now, if you allow users to choose ad hoc date ranges for these rollups, it may force you to do some ad hoc analytical queries that are very time-consuming. However, if you only allow set ranges, such as weekly, monthly, quarterly, and yearly, then the rollup sums can be aggregated in the data sets ahead of time, and the actual query to display them will be much more efficient. Now, I've worked on a system in which this decision on rollups was actually made for efficiency. I've also worked on a system in which the user wanted tens of thousands of historical data points to appear on a single trend. Now, we convinced the customer that such dense data would not be readable on a trend. The trend was only a few hundred pixels across on the screen, so there was no way that tens of thousands of individual data points would even be distinguishable. We therefore only showed the most important few hundred data points instead. The point being, analytical workload efficiency can be managed via importance, but should also be made individually efficient. Cloud technology is very good at scaling out process-intensive work for maximum efficiency, and Microsoft Azure has a solution for running process-intensive batch jobs called Azure Batch. In this video, we're going to take a closer look at Azure Batch. Azure Batch allows you to create and manage pools of virtual machines to run your process-intensive batch jobs. You can also write your own application code, such as scripts that process data, and install them into Azure Batch to be run on those virtual machines. Then you can schedule jobs to run your applications against the data and output the results. Developers can integrate Azure Batch into their own solutions. For example, if you have an application that searches images for particular patterns, you can set this up in Azure Batch. There are many applications for Azure Batch. Any intrinsically parallel workload, that is, where the workload can be easily broken into distinct, independent subjobs, is ideally suited to Azure Batches, since each subjob can be run concurrently on a different virtual machine. Some of the many applications ideal for Azure Batch are risk modeling, which is mathematically intensive, image processing, since each image can be processed pixel by pixel by concurrent processes, optical character recognition or OCR, which identifies text characters in an image and is a specific form of image processing, 3D rendering, where groups of 3D objects can be processed concurrently, data ingestion, where large amounts of data can be transformed, and software testing, which happens in batches and consists of many independent tests that can run concurrently. Azure Batch also enables tightly coupled workloads. Tightly coupled workloads are workloads that rely on communication with one another. Many AI applications qualify as tightly coupled workloads. You can run concurrent tightly coupled workloads in parallel for high throughput. As an example, you might have a set of tightly coupled scripts that simulate well pump performance. If you have a field of 100 wells, Azure Batch could run the simulations of the wells in parallel. The only limit would be the configuration of resources for the Azure Batch instance. Azure Batch contains message passing interface APIs, specifically designed for passing messages between tightly coupled workloads. You have your choice of either Microsoft or Intel MPI APIs. There are also options for improving application performance if this is a concern. You can choose to use high-performance computing or HPC virtual machines for your workloads. You can also choose to use virtual machines optimized for graphics processing units or GPUs. Over the years, GPUs have become very performant for graphics and gaming, so are useful when workloads such as real-time 3D processing require extremely efficient processing. Some other Azure Batch capabilities are support for large-scale rendering workloads including 3ds Max and V-Ray, and the Do Azure Parallel R package, which scales out R algorithms. Data transformation with Azure tools such as Azure Data Factory is also a very popular use of Azure Batch. Now let's step through a common use strategy with Azure Batch. First, you need to upload the input files containing your process data, as well as the applications you need, such as scripts, to an Azure storage account. Next, you have to configure the pool of compute nodes, which are the virtual machines that are going to run your process. Add a job that will run the workload on the pool, and then add tasks to the job. The job's tasks will be specific to the steps for your particular process. You can control the virtual machine pool size for cost, and there's also automatic scaling when your workload grows and shrinks, and this will make CPU usage more efficient. Azure Batch then downloads the data and the applications to the node that's assigned to each task, and it will execute the task on the node using the application provided. You can monitor Azure Batch as it runs by querying the Batch Services HTTPS API. You can configure Azure Batch to upload the task output to an Azure storage account, where it can be downloaded by your other applications and services. Azure Batch has other options as well, such as running several tasks concurrently on one node, or running assigned job preparation and completion tasks for setup and teardown of each task. There are two main strategies for analyzing big data as it flows into a cloud system. You can analyze large sections of the data once it's already been collected and is in a data store. This is called batch processing. Another strategy, which lends itself to solutions that require very low latency, is real-time processing. Unlike batch processing, real-time processing endeavors to perform analysis on streaming data, which is data sequentially entering the system from some source before it's at rest in a destination data store. To glean business intelligence from it, real-time or near real-time, usually within seconds or even milliseconds. As an example, imagine temperature readings streaming from a thermostat device into a cloud solution. Now imagine there's someone watching a dashboard, and they want to know within a few seconds whether that thermostat goes over a critical threshold temperature so they can take action. This is an ideal scenario for real-time processing. The data stream from the thermostat can be monitored, and the moment the real-time processing determines that the temperature has crossed the threshold, an alert can be recorded which appears on the dashboard. Output from such real-time processing is sometimes stored in a data store for future use, and sometimes it simply streams directly to the visualization destination, such as a dashboard in this case. The key to real-time processing is speed. Data is flowing in via an ingestion pipeline, and the processing can't seriously affect the flow of that pipeline, or incoming data will back up, and the entire system will no longer be real-time. The trick to quick processing, besides the design of the processing itself, is usually a high degree of parallel processing. The incoming stream is split into substreams that are then processed concurrently by different instances of the real-time process. Another aspect that affects real-time processing is writing the output of the processing to its destination. Data stores for real-time processing have to be tuned for high-volume writes. The whole goal of this streamlining for speed is to present the results of the processing real-time to the user. Now let's look at the architecture of real-time processing. We'll start by considering the goal of processing data in big data solutions in general, and then work our way to how real-time processing fits in. The main goal of processing big streams of data is analysis, in which important trends are found in the data, and reporting, or getting the details of the data, usually in summary form to users. While some analysis and reporting is less real-time and can therefore be run against historical collected data, such as quarterly reports, some analysis and reporting is very time-dependent. Alerting on live critical conditions on a gas plant, for example. Real-time processing is designed for these sorts of use cases. Real-time processing architectures have an analytical data store, which is where they write the output of their processing. This data store is being updated real-time, as is the nature of real-time processing, so must be able to handle high-frequency data. This data store might be a typical database like SQL Server or Azure's Cosmos DB, or it might be a temporary data store that only keeps a certain window of real-time data at any moment. An example of this might be Microsoft's Power BI, which is capable of acting as a real-time data store, where visual trends show the latest real-time data output streaming from a real-time processing service. Real-time processing requires real-time message ingestion that's capable of keeping up with the demands of the processing and maintaining real-time or near real-time throughput. If ingestion backs up too much, for instance, if a real-time process is meant to alert a user to a critical situation within seconds, and the ingestion is backed up by several minutes, the benefits of real-time processing are lost. And the heart of real-time processing is the actual processing of the stream. This is some sort of logic that analyzes data as it streams in. It can perform many different processes on the incoming stream, such as filtering, aggregating, or transforming the data in some other fashion before sending it off to the data store for analysis. So let's take a closer look at the different aspects of a real-time processing architecture. First, the ingestion of data. There are different technologies that are tailored to real-time data ingestion. We'll take a look at a few offered in Microsoft's Azure Cloud Platform. Azure Event Hubs is popular for ingesting millions of events per second. It speeds up processing by doing processing in parallel, while also guaranteeing the order of events as they flow in. Azure IoT Hub is another option. It supports bidirectional communication with millions of Internet of Things or IoT physical devices. And Apache Kafka is an open source option for stream processing that also handles millions of messages per second. In many real-life architectures, these ingesting technologies are combined to achieve specific ends. For example, I've worked on architectures that use Azure IoT Hub for ingestion of physical device data, and then feed that data to an Azure Event Hub for further processing by multiple downstream services. There are some real-time processing architectures that take advantage of static data stored in a data store. For example, if you're comparing streaming data to thresholds for alerting purposes, you may have those thresholds stored in a static data store. You may also want to archive incoming stream data for downstream processing other than real-time processing, such as further batch processing. In these cases, you'll want to use a suitable storage technology, such as Azure Storage Blob Containers or Azure Data Lake Store. Real-time processing works by ingesting, processing, and finally outputting stream data. Now that we've looked at the ingesting side, let's discuss processing. There are several options for the real-time processing. Azure Stream Analytics is Azure's solution. It allows you to write your processing logic in a SQL-like language that's extendable via JavaScript. Apache Storm has its own architecture that uses code modules called spouts in ingress and bolts for processing and output. It supports code in C# and Java. And Apache Spark is another option which supports Spark languages, such as Java, Python, and Scala. One commonality of these technologies is they support high performance through massive parallelism. Basically, they break incoming streams into independent substreams, which can be processed concurrently. To understand how this works, imagine an architecture connected to millions of physical IoT thermostat devices installed in customer homes, and each thermostat sends a new temperature reading to the cloud every second. If the real-time processing had to process all that data as a single incoming stream, it may have trouble doing it real-time. But every thermostat is a separate, independent device, and therefore the data for each thermostat represents a single independent data stream. So thousands of real-time processing instances can be spawned, each dealing with only one or a subset of incoming thermostat streams. This is called horizontal scaling and can dramatically speed up processing time. The output of this real-time processing goes to some data store, and there are many options of data store to choose from depending on your requirements. Azure Synapse Analytics is an entire analytics service that can ingest data from a real-time process. Another analysis service from Azure is Azure Data Explorer, which excels in ad hoc analysis of the resulting data. Some Apache options are HBase for NoSQL, or if the data is stored in files, it can be queried via Spark or Hive. Once the real-time processor has prepared the data for analytics and it's been stored, you need tools for analytics and reporting. Azure Analysis Services will allow for analysis and reporting on historical data, and if that data is being updated fast enough by a real-time processing pipeline, it can simulate near real-time. Power BI can also report on historical data, or a real-time processing pipeline like Azure Stream Analytics can stream its output directly to it, and Power BI can display the data on a live trend. And you can also pull the real-time data into tools like Microsoft Excel for further analysis. The goal of big data solutions is to analyze vast amounts of data for trends and insights that have value. In the context of large organizations, they're usually searching the data for business value. There are two main forms of data processing in these systems. First, raw data is ingested and, if necessary, converted to a meaningful state. Then the data can be processed near real time as it arrives. This is called streaming data, and the process is called stream or real-time processing. The processed data may then be stored and further analyzed. Another method is to store the data and then analyze the historical data in groups. This is typically not real time. The data may be analyzed hours, days, or even years after it's been collected. This is called batch processing. In this video, we're going to compare and contrast stream and batch processing. Then we're going to look at a growing trend in data processing, operational intelligence. So let's compare processing of batch versus streaming data. First, they differ in data scope. Batch processing has access to all historical data, so the data scope can be very large. As an example, batch processing might be run on an entire year's worth of data to determine beneficial trends over the year. Stream processing, on the other hand, works on a much smaller data scope, usually the last few seconds of incoming data. For example, a stream processor meant to alert for anomalies in the temperature of an HVAC unit might look at all incoming temperature data streaming in from an HVAC sensor, but it may only examine a rolling window of 30 seconds of data at a time to find real-time anomalies. The data size is also different. Batch processing is made for performing a process on very large data sets. Stream processing, on the other hand, is designed for processing very small batches of records, usually only a few seconds worth as they stream through. The expected performance is also vastly different. Batch processing occurs out of band of data ingestion. Basically, it processes on historical data in a data store, not on live streaming data. Batch processes can commonly run for minutes, hours, or even days. They're often scheduled and not expected to complete real-time or even near real-time. Stream processing, on the other hand, is meant to perform as real-time as possible, so is expected to run in a matter of seconds or milliseconds. Batch processing can perform complex analysis, since it's not seriously restricted either on data size or runtime. Stream processing, on the other hand, has to be very performant, and so is regulated to relatively simple analytics, such as rolling averages or detecting fairly simple anomalies. So to summarize, batch data is for processing large data sets and performing complex analytics that may take hours or longer to complete. An example might be determining the optimal configuration of HVAC settings for a building by collecting a year's worth of historical data on the building's units. The large data set enables the complex analysis, which in this case might involve machine learning. On the other hand, stream processing on streaming data is to do simple analytics in real-time or near real-time on a data stream as it arrives. It's excellent when a quick response is required. For example, a stream processing service might text an engineer within a few seconds of a gas plant pressure reading going out of normal. So far we've discussed stream processing in its simplest form, where the processing is a single stream. There's a more aggregated version of stream processing called complex event processing, or CEP, which combines the data from many streaming sources. It detects patterns, such as business opportunities or threats to the system. These significant events, gleaned from multiple types of data, are determined near real time to allow for fast response. So you can think of complex event processing as stream processing taken to a higher level, where multiple data sources, usually representing various different types of data, are considered together, allowing the quick discovery of useful data patterns that would not be apparent if the streams were analyzed in isolation. This brings us to the concept of an operational intelligence, or OI system. An operation intelligence system combines real-time data processing and complex event processing by performing near real-time analytics on various data streams to offer the sort of business insight that a business intelligence or BI system would offer. The big difference between a BI system and an OI system is that the BI system searches historical data, and so its insights take a long time, while the OI system is meant to give near real-time insight that exposes business value across the organization's various data streams. This type of real-time operation intelligence offers customer experience optimizations, such as giving personalized service based on the previous interactions the system has collected. Since it considers a wide range of data, it can offer a total customer experience. OI systems are often used for point of sale. They can offer real-time inventory, the history of items in the store such as their customer satisfaction ratings, and real-time information such as how many items are available for sale. Another use for OI systems is analyzing social media. An organization could scan their various social media feeds to identify negative reviews, for instance, and quickly respond. Data storage is a very important aspect of big data solutions. In this video, we're going to look at the most popular type of database around, a relational database. As the name suggests, a relational database stores and provides access to data points which have relationships to one another. Furthermore, those relationships are strictly defined in what's called a relational model. This data is organized into tables, in which the rows represent individual data points. Relationships of data points within the table, as well as relationships between tables, are represented by unique IDs called keys. And the properties of the data points are represented by the columns of a table and are often called attributes of the data point. As mentioned, relational database structure is rigid. This structure, also called a schema, defines the logical organization of the data into tables, and it must be defined prior to the data being stored. Although the schema can be modified with some manipulation of the data after the data has been stored. This logical organization can be very different from the physical organization of the data, and this decoupling of logical structure and physical storage is important. It means that database administrators can, for instance, re-index the data, which means reorganizing it physically for more efficient processing, without modifying the logical organization. The database structure consists of data tables, which, as mentioned, store data points as rows, where the attributes of the data points are defined as columns. Views, which are like a predefined query that returns the data in a different organization than the logical structure. And indexes, which help improve data retrieval. So what are some of the benefits of having data rigidly defined in table structures? Well, first of all, it's an intuitive way to store data. For example, if you have a table of users, a user being the data point, and the attributes of a user are their username and password, if you view this data as a two-dimensional table, with rows being users, and attributes like username and password being the columns, it's easy to read. You can scan the records up and down to find a user, and read that user's attributes left to right. The relational database model offers efficiency in reading and writing data. Typically, tables have a primary key, which is a unique identifier for each row. This gives a foolproof way to find a row. In the user table, for example, the username could be the primary key because it must be unique. The table structure guarantees that you cannot store two rows with the same username. Tables can also have multiple keys, and these can be stored in an index table for quick reference, which makes looking up individual rows more effective. And the model is flexible. There is no one model, but instead, the database designer can define a model that fits the data. There are literally endless applications for relational databases. Long before cloud systems emerged, relational databases were used as the back-end data store for most applications. And even today, relational databases are still the most commonly used. Databases that were once strictly on-premises, such as Microsoft SQL Server, have been ported to the cloud. A few examples of applications that use relational databases are applications for tracking inventories, since inventory items have set attributes and well-understood relations to one another. Process transactions, again because the attributes are well known and relational databases are excellent at consistency in data. And managing customer information, since each customer can easily be represented as a row in a table. As I briefly mentioned, data consistency is the hallmark of the relational database. Consistency means that anytime you query the database, you'll get the most up-to-date data. Relational databases can offer strong data consistency within an instance and also across multiple instances. Say in the case of a cloud deployment where the database is replicated in different regions. On the other side of the coin, there's been a surge of popularity in non-relational databases in the cloud, such as NoSQL databases, which trade consistency for other desirable traits that relational databases are less successful at, such as elastic scalability and speed. These non-relational databases offer what's called eventual consistency, meaning that there may be some time after a data change is made that a query might return an old state, and the return data is not completely up to date. But after a certain period of time, the data will be consistent. Which type of database is used depends on the specific requirements. Relational databases are also programmable via stored procedures. These procedural scripts can automate common, repeating actions, such as making sure strings are in a specific case. Stored procedures can generate data in the tables derived from other data. For instance, when a user is entered with a first and last name, a stored procedure might automatically populate an attribute called name, that is the last name followed by a comma followed by the first name for display purposes. When guaranteeing consistency, relational databases need to take into consideration concurrent users. Database locking is the process of locking out other concurrent users while a current user is accessing the data or updating the model. Some databases lock on the table level, which can seriously affect performance if many concurrent users are trying to access the same table. A more efficient manner of locking is locking only the rows being accessed. User concurrency needs to take not just database locking into consideration, but also management of permissions for the various users to view the data or perform actions. There are several factors to consider when choosing a database. What are your data accuracy needs? For instance, are you writing banking software where consistency needs to be guaranteed? Or are your consistency needs less stringent? Say, if you're writing software that reports analytics on social media posts, and eventual consistency is acceptable. What are your scalability needs? How big is your data going to get, and can the database support it? How many users will be using your system concurrently, and will your system support data accuracy with this concurrency? And what sort of performance and reliability or uptime do you need to guarantee? These questions will help you determine what type of relational database solution is best, or if you should look at non-relational solutions. So in this course, we've examined core data workloads and workload management. We did this by exploring workload management, data solutions, and data storage types and needs, transactional and analytical workloads, Azure batch and real-time processing, differences between batch data and streaming data, and relational data. In our next course, we'll move on to explore Azure Data Analytics by using Azure Data Explorer, learning about data visualization and reporting, extract, load, and transform or ELT processing, and extract, transform, and load or ETL processing.